There is a moment in every great journey where the traveler crosses a threshold that cannot be uncrossed. A point where what lies behind and what lies ahead become fundamentally different environments, and the act of passing through that boundary changes the nature of the journey itself. For Voyager 2, that moment arrived on November 5, 2018, at a distance of approximately 11 billion miles from Earth. On one side of that invisible line was the Sun, its solar wind, its magnetic field, its charged particles, and its protective influence. On the other side was something no spacecraft had ever directly measured from within before: the interstellar medium, the plasma between the stars, the ancient environment beyond the region controlled by our Sun. Voyager 2 crossed that line. And what it found on the other side forced scientists to rethink parts of the picture they had built over decades. This is not a story about a mystery that nobody can explain. It is a story about a boundary that physicists had been theorizing about for decades, a boundary we thought we understood, and a spacecraft that showed us how much more complicated it really is. To understand what Voyager 2 found at the edge of our solar system, we first need to understand what that edge actually is. Most people think of the solar system as ending somewhere around Pluto. That makes sense because Pluto was once considered the outermost planet, and most diagrams of the solar system stop around there. But Pluto is nowhere near the physical edge of the Sun's influence. The Sun does not simply provide light and heat. It continuously releases a stream of charged particles called the solar wind, flowing outward in every direction at hundreds of kilometers per second. That solar wind creates an enormous bubble around the planetary system. That bubble is called the heliosphere. Inside it, the solar wind and the Sun's magnetic field dominate the particle environment. Everything from Mercury to Pluto and far beyond exists within a region filled with material originating from our star. The outer boundary of this bubble is called the Heliopause. It is the region where the outward flowing solar wind meets the surrounding interstellar medium. Beyond it, the environment changes dramatically. The particles are no longer dominated by the solar wind. The magnetic environment becomes increasingly influenced by the interstellar medium, and Voyager is effectively traveling through the space between stars. Voyager 2 took more than 4 decades to reach that boundary. It launched in August 1977, flew past Jupiter in 1979, Saturn in 1981, Uranus in 1986, and Neptune in 1989. Then it kept going. For decades, the spacecraft continued traveling outward, gradually moving farther and farther from the Sun. Then, on November 5, 2018, Voyager 2 detected the unmistakable signature of crossing the Heliopause. Its measurements of solar wind plasma dropped away. Galactic cosmic rays increased. And the spacecraft entered a fundamentally different particle environment. Voyager 2 became only the second spacecraft in history to enter interstellar space. Voyager 1 had done it first, crossing the Heliopause in 2012 from a different direction. But Voyager 2 had something extremely important that Voyager 1 no longer possessed. Its plasma science instrument was still working. Voyager 1's plasma instrument had stopped functioning decades earlier. That meant Voyager 1 could measure the crossing using its other instruments, including its magnetometer and cosmic ray detectors, but it could not directly measure the plasma environment in the same way. Voyager 2 could. The instrument built in the 1970s was still operating more than 40 years later. And when Voyager 2 reached the Heliopause, scientists finally had a functioning plasma instrument watching the transition in real time. The first major surprise was the sharpness of the boundary. For decades, models had suggested that the transition between the solar wind and interstellar plasma would be relatively broad. Scientists expected the two environments to blend across a large region, more like two rivers gradually mixing together. Voyager 2 saw something much sharper. The transition occurred over a remarkably short distance. One day, Voyager was inside the Helios heath. The next, it was measuring plasma characteristic of the interstellar medium. The Heliopause was not simply a vague fading edge. It behaved much more like a distinct physical boundary. The second surprise involved the interstellar plasma itself. Scientists expected the material outside the heliosphere to be extremely cold. Instead, Voyager 2 measured plasma conditions that were warmer than some models had predicted. The local interstellar environment also turned out to be more variable than the simple picture of a cold, uniform void suggested. The third major discovery involved magnetic fields. Voyager 2 detected evidence of a magnetic barrier near the outer region of the heliosphere. The magnetic field became stronger in the region surrounding the boundary, creating a zone of enhanced magnetic pressure. That matters because the heliosphere is not just a bubble of solar particles. It is also a magnetic shield. Cosmic rays produced by supernovae and other energetic events throughout the galaxy constantly travel through interstellar space. Many of these particles move at almost the speed of light. The heliosphere helps reduce the number of these high-energy particles that reach the inner solar system. The magnetic structures around the heliopause play an important role in that shielding. Voyager 2 helped reveal that the interaction between the heliosphere and the surrounding interstellar magnetic field is much more complicated than earlier models suggested. Then came another major realization. The heliosphere is not perfectly symmetrical. Voyager 1 and Voyager 2 crossed the heliopause at different locations and in different directions. If the heliosphere were a simple spherical bubble, both spacecraft should have encountered nearly identical conditions. They did not. The two spacecraft found differences in the magnetic field, plasma environment, and structure of the boundary. That showed that the heliosphere has a complex shape determined not only by the solar wind, but also by the direction in which the Sun moves through the galaxy and the properties of the interstellar medium surrounding it. The Sun is moving through the galaxy. The interstellar medium is flowing around the heliosphere. And the result is not a perfect sphere. It is a dynamic structure. A bubble shaped by the constant interaction between our star and the galaxy around it. That discovery matters for another reason. If the heliosphere changes shape depending on the surrounding interstellar environment, then the amount of protection it provides against cosmic radiation can also vary. The inner solar system is not sitting inside a perfectly stable shield. The heliosphere responds to solar activity and to the environment through which the Sun travels. If the Sun enters a region of denser interstellar material or stronger magnetic pressure, the heliosphere could become more compressed. A smaller heliosphere could allow more cosmic radiation to reach the inner solar system. This does not mean Earth is currently facing a dangerous change. Voyager's measurements do not predict an imminent threat. What they do show is that the protective environment around our solar system is more dynamic and complicated than earlier models suggested. And that changes how scientists think about the long-term relationship between our solar system and the galaxy around it. Another important finding came from the interaction between the solar wind and the interstellar medium. The two environments are not completely isolated. Solar disturbances can travel outward and eventually interact with material beyond the heliopause. Voyager 2 has detected changes in the interstellar environment associated with solar activity, showing that the Sun can influence space beyond the boundary of its own heliosphere. In other words, the heliopause is not a wall. It is an interaction zone. The Sun reaches beyond its own bubble, and the galaxy pushes back. Voyager 2 is now measuring that interaction from the other side. The 5 major research papers published together in 2019 brought these observations into a single scientific picture. A sharper boundary. Unexpected plasma conditions. A magnetic barrier. An asymmetric heliosphere. And a more complicated relationship between the solar magnetic field and the interstellar magnetic field. None of these discoveries meant that physics had failed. They meant the models were incomplete. And that distinction is important. Science advances when observations force scientists to improve the model. Voyager 2 became a pathfinder because it went somewhere no spacecraft had directly explored before and returned measurements that changed our understanding of that environment. But the story did not end when Voyager 2 crossed the Heliopause. In many ways, that was only the beginning. The spacecraft is still traveling through interstellar space.